So far we've been talking about stress and strain. Let's talk about how we start measuring strain. And to measure strain, we use something called a strain gauge. But before we get to that, let's think about how a strain gauge actually works so we can inductively think about how they actually work and what they're actually doing. Now, if we take a piece of wire, we understand that that wire has a small amount of resistance. Normally, a wire will have very little resistance because we want it to carry electrical signal and we don't want too much of that electrical signal to be wasted as heat, for example. Now, we can actually compute the amount of resistance in that wire as follows. We say rho, which is the resistivity of the wire, which is measured in ohm meters. We multiply that by the length of the wire, and we divide that by the cross-sectional area of the wire. Now, this is one of the reasons why if we have really, really long wires, we're going to lose a bit of voltage. There's going to be a voltage drop over that wire because the resistance of that wire is increased. If we make that wire a whole lot shorter, the resistance is very, very low because we've got less of a distance, that length that wire travels over to actually create a resistance there. Likewise, if we want to reduce the resistance of our wire, we could make the wire with a larger cross-sectional area, which will deal with the bottom part of that equation. Or we could have multiple wires and put them all side by side. In doing that, we've also essentially increased our cross-sectional area and reduced our resistance. Now, different materials have different resistivities. And you can see a whole bunch in this table, from things that are actually really good conductors, and you've got things like silver and copper and gold here, to things that are really, really good insulators, like sulfur and rubber and quartz. And you see them in everyday life. This is why we don't use sulfur or glass or something like that in our wires. And this is why we don't use something like copper or gold in our insulators, because they do the opposite of what we want them to do. So we choose these materials that have a low resistivity to be our conductors, and we choose these materials that have a high resistivity to be our insulators. Now, we'll be talking more about those things that have lower resistivities for the purpose of understanding what strain gauges do. What's the strain gauge then? Well, I mentioned we want to measure strain. And so what we want to do is convert strain into, which remember is the deformation of an object or material, into some sort of an electrical signal so that we can easily measure what it actually is. Well, the way we do that with our strain gauge is it converts that deformation into a change in resistance. And the way it's done is, think about a wire. We have a piece of wire, and if we stretch that wire, so we're essentially putting strain on that wire, we stretch it out, it'll get slightly longer, ever so slightly longer. Now, when we make it longer, we're reducing the cross-sectional area of that wire. It's getting smaller. As we reduce the cross-sectional area of that wire, remember our equation before? The cross-sectional area was on the bottom of the equation. Our resistance increases. So we reduce cross-sectional area, resistance goes up, just by a little amount. What we can then do is infer from the change in resistance the amount of strain, or how much we've managed to stretch our wire. Let's move over to actually strain gauges. So essentially, we're working out how much a wire is stretched, but that wire is only going to be stretched by a tiny amount, and hence the resistance is only going to increase by a tiny amount. So what we do is we create a gauge that looks a bit like what we've got above. And that gauge has a whole lot of wires, which allows not just one wire to stretch, but a whole lot of wires to stretch simultaneously in the same plane. And in doing so, we've essentially amplified that effect. We've made it larger. Doing so, it's a lot easier to see our change of resistance in that wire, because we've done it not just one time, but many times. We've essentially stretched many wires. And when we've done that, we've got our resistance increasing all the more. Of course, still not by a huge amount, because this stretching is occurring at a very fine scale. Now, I should mention we've got our stress strain curve there, and we're only wanting to work in these strain gauges in that elastic region there. We're not wanting to work in the region where we essentially break the strain gauge. And I've done that before. accidentally having a robot that was measuring strain in sewer pipes, and it fell off the table or fell out of a sewer pipe onto the floor. The strain gauge hit the ground and actually deformed it out of position. And when I bent it back again, it was never working again. That was a brand new gauge required there. And so we want to work in that elastic region where we're not applying too much force, because if we apply too much force to it, we break our strain gauge and it's not going to work. Now we've got this thing called the gauge factor, and the gauge factor is a ratio of the change in resistance to the nominal resistance when no stress has occurred, divided by the change in length by the nominal length, the length when no stress is applied. And so these things will both be quite small. Our change in resistance will be in the order of a few ohms. Our change in length will be in the order of tenths of millimeters, or maybe a millimeter at the most. They're very small amounts. And our strain we can measure as 1 on the gauge factor, so 1 on K, multiplied by the change in resistance over the nominal resistance. What's the resistance of that strain gauge when no force is actually applied to it? That's what we call our undeformed strain resistance. Well, let's look at a few different materials that are actually used for strain gauges, and there's a few different ones around. The most common ones are those nichrome ones, where our gauge factor is just over 2, 2.1 to 2.6. And you'll notice that at the right-hand side, there's a temperature coefficient of resistivity. And the reason for this is our resistivity actually changes with temperature, which is an interesting thing that we'll be coming back to and working out how we can actually correct for that. Now, there's a few other different gauges there, from silicon ones to germanium ones as well. We'll concentrate most of our time on those nichrome ones though. Having said that, it's interesting to think back about the history of strain gauges and where they actually came from. They were invented by 2 different engineers at the same time independently, which is kind of weird. So Simmons was at Caltech and Rouge was at MIT. One an electrical engineer or electronic engineer, the other a mechanical engineer. And they actually invented them for different purposes because they saw a need in their laboratory trying to measure one thing. Simmons was trying to measure behavior of metals when they were under shock. So when a shock was applied to them and looking at the behavior of them. Rouge had big water tanks that was measuring vibration on them through vibration tables and looking at seismic measurements about earthquakes and things and how they affected these water tanks. And it's interesting that when the patents were awarded, they were actually jointly awarded, even though these people discovered this technology independently. You see a picture there of one of the first strain gauges, or one of the early strain gauges, the SR4. And what they actually did is they actually labeled the name of the strain gauge, SR, for standing for Simmons and Rouge, and 4, they had a number of lab techs that were helping them out. And so there are actually 4 inventors in the whole process. But these have been around since the late 1930s. So it's a fairly old and mature technology that's been used for, well, almost 90 years. And some of the early uses, they were using them on things like buildings and measuring force in buildings. And later on, they were soon used on aircraft and measuring forces on aircraft wings and trying to look at the force of those wings under different flying conditions. These days, the most common strain gauge we use are these foil type strain gauges. And there's a number of different orientations of these gauges and formats of these gauges based on whether we want to measure on a single axis or a double axis or a triple axis or a whole array of these strain gauges. Lots of different ways these are assembled and used in real life. And these are different sizes, from tiny, tiny, tiny gauges to larger gauges, depending on the measurement area that we're trying to measure over.